Today we're looking at 11.3 area of polygons. Our essential question: how can you find the area of a regular polygon? Remember, a regular polygon is a polygon where all sides and angles are congruent. So first, starting off, defining a couple things. Our center of a regular polygon is the center of the circumscribed circle. So the circle that goes around and touches each vertex on the outside. Right, that's the center of that circle, is the center of our polygon. Our radius is the distance from the center to a vertex. So it's going to be the same thing as the radius of your circle, or the same length. So GE here is a radius. GF would be a radius. GC would be a radius. GH is not, because H is not a vertex of our polygon. So you only have a certain number of radii in your polygon. Then probably a new term, apothem, A-P-O-T-H-E-M. That is the perpendicular distance from the center to a side. So side G, segment GH here is an apothem. And then we have our central angle, which is a little bit, it's still at the center, like in a circle, but it's a little bit different. It's an angle formed by two radii with consecutive vertices. So angle EGF is a central angle. Angle AGB would be a central angle. But angle HGF would not be, because H is not a vertex. And angle AGC would not be, because A and C are not consecutive vertices. Okay, so those are our main terms. Example 1 says find the measure of a central angle of a regular polygon with a given number of sides, and they say 18 sides. So we look at our full circle here. We have 360 degrees. That's going to be cut into an equal number of sections by the number of sides we have. So in this case, 18. So 360 over 18 gives me that each angle is 20. Then example 2 asks us to find each part here. So angle EGF, that is our central angle. We have 6 sides, so we do 360 divided by 6. Gives me 60 degrees as that angle. Then they ask for EGH. Okay. The apothem is always going to cut that central angle in half because it hits at 90 degrees, and that's an isosceles triangle. So that the apothem in every one of our regular polygons will cut it in half. So I take that angle we just solved for, I cut that in half, I get that as 30. Then angle HEG is this angle over here at E. We have a triangle here, right? We just said on this one that this angle up top is 30. This is 90. So if I take that away from 180, I get that this angle at E is 60 degrees. Okay. Those numbers are going to be true, not something you would need to memorize, but those angles are going to be true in every regular hexagon. As we come down and look at, like here we're looking at a pentagon. Here we're looking at an octagon. All right. So, oops, you couldn't see where I was pointing. All right, here's a pentagon, here's an octagon. So those numbers are going to be different than what we just solved for. But if you solve for those, they would be consistent in those things. Then area of a regular polygon. So area of a regular polygon, this is area of a regular n-gon. That means it works for any number of sides. With side length S is 1/2 the product of the apothem and the perimeter. Okay, so we give it that formula here as A equals 1/2 apothem times perimeter. More often than not, you'll see it as A equals 1/2 A times N times S, or when I'm going through it, I just switch those letters. I don't know why I do that, but I do 1/2 A S N. All right. So S times N, or N times S, that is giving me the perimeter side length by the number of sides. So then example 3 is asking us to find the area of the regular polygon. The thing that happens on some of these is sometimes they don't give you exactly what you need. So you need to check that. So when I look at A, they give me the apothem is 6.5. I can count my number of sides is 5, but I don't have my side length. So these are always going to be right triangles. You could see problems with trig or special right triangles. We'll mainly be dealing with Pythagorean theorem. So here I have 6.5. I have my unknown part here, and I have 8. So I do 6.5 squared plus x squared equals 8 squared. Solve that out. I get x is 4.67. But x is just this part. So I need to double that to get 9.34 for the side length. So I have 1/2 my apothem, my number of sides, and my side length. And then this is my area, 151.78. We look at the next problem. We said this was an octagon, right? So I have 8 sides. They give me the side length is 3. But this goes to a vertex. So that is not my apothem. That is my radius. So if I draw the apothem in here, right, that hits here, it's going to cut that 3 in half. So I have 1.5 squared plus a squared equals 3.92 squared. Okay, that's the setup to find my apothem. Solve that out. I get my apothem is 3.62. I plug that in, so I have 1/2 times my apothem, 3.62, times my side length, my number of sides, 8, times my side length, 3, gets me 43.44 centimeters squared. Right, so 3 more examples here. C, we have our, well, they give us the radius is 6. All right, they don't give me my apothem or my side length. So in this case, the central angle, 360 divided by 3, gives me that this central angle is 120. So if I look at this triangle right here, which I redrew out over here, you have an angle of 60, an angle of 30, and 90. So that is our 30, 60, 90 triangle, and our hypotenuse is 6. So my short leg is half of that, which is 3. My long leg is root 3 times that, so 3 root 3. I need to double that for my side length, which is 6 root 3. So I have 1/2 times 3, which is my apothem, times 3, which is my number of sides, times 6 root 3, which is my side length. That gets me 27 root 3. You could get that out in decimal form, but if you just do 3 times 3 times 6 and divide that by 2, you get 27. You don't even need to deal with the root 3 there. Now then, D and E are nicer ones. These are the ones we like. They give us everything we need. So here I have a apothem of 30. I have a side length of 10. I can count my number of sides, which is 12. So I plug in 1/2 times 30 times 12 times 10, and I get 1800 as my area. On E, they give me an apothem of 7, a side length of 3, and a number, again, I could count my number of sides. My number of sides is 9. So I plug those in. I get an area of 94.5. Then the other thing we look at here is area of a rhombus and a kite. Area of both a rhombus and a kite is 1/2 diagonal 1 times diagonal 2, where D1 and D2 are my diagonals. So I'm looking at A here. I did 1/2 times 50 times 60 is 1500, right? 50 is this diagonal, 60 is that diagonal. One of the things to watch is that they're actually giving you the diagonals. In both A and B they do, right? We have 1/2 times 18 times 21 in B, but in C I have 12 as half of that diagonal, 18 as half of that diagonal, so I need them. Now this is a kite, so the this is a rhombus, so the diagonals are equal. So I can just double that. 1/2 times 24 times 36 gives me my area of 432. Okay. On D, they give me parts, they don't give me everything I need, and I have a kite. So here, this is 12, right? This is going to be equal and be 12. Oh, actually, I solved this as 12. All right, they give me 20, 16, and 30. So I don't know this length. Fortunately, they're the same, so I don't need to do the math once, but I need to do Pythagorean theorem to find that. So I do 16 squared plus x squared equals 20 squared. I get that this is 12. So this side here is 24. This side here, I need to add 16 plus 30. So I have 1/2 times 46 times 24 gets me an area of 552.